Hello everybody, this video is about regression in Jupyter Notebook. So for the sake of time I type some codes here. These are things that are already known. I made some videos on how to import data, how to load and read data in Jupyter Notebook, and also how to prepare the input to output feature, as well as how to split the data set into training and testing data. So I prefer, for the sake of time, to write them here and go quickly. So the first thing you need to do is to load the data. To load the data, we need to import the library as SPD. It's here, and we read the data. I call flood. This is the object name. We call pd.read underscore CSV. This is the directory of my dataset on my computer. This is the name of the dataset with the extension CSV, comma separated value. And this code is going to read it, and this is going to, the second code, flood.shape, is going to give me the shape. It means how many rows and columns I have in the dataset. So let me run. So I have here 4017 rows, which are the observations, and 20 columns, which are the features, the number of features. So number of rows is number of observation, and number of columns, the number of features. And the flood.describe is going to give the description of the data set. So this is the content of the data set. You have time, you have area, you have a specific humidity, SH. Area is the flooded area. This is our output. And we have the latent heat flux. This is the last one, the last feature in the data set. So this is the data, the description. And now we need to prepare the output and input features. So for this we need a NumPy library. So we import NumPy as np. We run, and then you have the output feature is y. Y is, I said, the output is the flooded area. So to have the output, you have np.array flood, the name of the data set. We take area in quote within brackets. So okay, I already run here. So you run here, you have this is one-dimensional array. So only area 4017 observation of area. So we come to the input features. X we call np.array flood.log. So log here we are going to slice take from a specific humidity, which is the first feature after area and the last latent heat flux. So we take all the rows from a specific humidity to latent heat flux. So if you see the data here, you have time, we exclude it, you have area. So after area is SH here. Then the last one is LHF. This. So run this code, and this code x.shape is going to give the shape of x. So x from SH to LHF have 18 features. So number of observations, so it's the same, 4017. Sorry. Okay. Now we need to split our dataset into training and testing datasets. And I've made a video about how to do it, so I prefer also to write it here. So we need this function train underscore test underscore split. So we need to import it from scikit-learn.model selection. So type this code. Then here we split the data itself. So we have x train, x test, y train, y test equal train underscore split underscore test underscore split x y. Take the test size as 30%. Here. So we run this, and this is going to give us the shape of the x train. 2818 and 2811 and 18. For the full 18 features, we have 2811 observation. This is the 70%. So the text is going to be the 30% now. It's 1206. So if you want for the y, you would have you type this, and you would have just one dimensional array because it's only area. So 2811 observation for only area. And then 1206 observation for area. Okay. So we already split our data into X into training testing data. Now we are going to feed the model. To feed the model, the rich regression model, we need to import rich, this module, and import it from scikit-learn.linear model. That's the first thing to do. We run. After this, we need to feed the model and apply the process for the training set. So we are going to fit it and train it on the training set. For this, let's give the model a name. read.flag equal we have rich dot parenthesis dot fit x train y train. Here alpha I let it this way. So already fitted here. The model is fit. So now we needed to see the model intercepts. To output the model intercepts. To do that, type the name of the model. Dot intercept, and then underscore, and we run. Which model did I run this? Okay, let me run first. Okay, which intercept equal read model reach flat, sorry. This is reach underscore flat dot intercept instead of model. Read model is not defined. Okay. Good now. Now this is the intercept. Beta 0. We now need the model coefficients. To output the model coefficients, we type the name of the model and the pair, the score. So we would have 18 from beta 1 to beta 18. So 5, 5, 10, 4, 4, 18. So the question for SH, and the last question is for LHF. Okay. So now you are going to output the R squares. The first on training data. Print the R squared on training data is, type the name of the model, reach is quote, comma, reach underscore flat dot score. We need the score on X train Y train and times 100. Okay, this gives us 75.55, 55%. Now we need it on testing data. We print the R square on testing, sorry. Data is, close the code. Now we give the name of our model, score. Score X test Y test multiplied by 100. Okay, they are very close, very close. Okay, so now we are going to plot plotting the prediction errors and the residual, plotting the prediction errors and the residuals. To do this, we need to import the standard scalar, because it's going to help us to standardize and scale the data. So from scikit-learn dot preprocessing import standard scale. Now we need to go to Anaconda prompts. Or even in the command prompt, in the type, this code pip install yellow brick. Okay, let's say here plotting the prediction errors and the residuals using yellow brick. Okay, so you need yellow brick, you need to install it, and to install it you go to another prompt, even the command prompt, and type pip install yellow brick. That's Anagona, and you come here to Jupyter, the type from scikit-learn preprocessing import standard scheduler. You run it. Okay. Now you plot the prediction error. To do that, you need to import prediction error function from yellowbrick dot regressor. Yellowbrick dot regressor import prediction error. From yellowbrick.regressor import prediction error. And run it. You type visualizer. You want to visualize the prediction error. So visualizer equal your prediction error in what? On the model reach underscore plot with the prediction errors there. Then you need to visualize it on the fit X train Y train. Okay, let's run this code by code. Okay. See the logo. Okay. The second, first for the model, second and Y train exchange is what you get. Second line of code. The third line of code is going to output the score, so you want to visualize. Get the score on X text, Y text. You train and then you predict. You see on, okay. This is to get like that. The errors mixed. Text and Y text. Then visualizer.proof going to show you the scores with the line of best fit. So you have identity, you have best fits here, these plots, you have error score here. Prediction error for each. So after getting that, the second thing is to get your residual plots. So plotting the residuals. This you need from yellowbrick. regressor, residual plot. So from your regressor import residual plot. So you repeat the same thing again. We need our visualizer this time. We call residual plots of our model, which is reach flag underscore flag. And then visualizer dot fit x test y test. No, the x train y train, sorry. Okay. Then we need to output the scores, visualize them. On X test, Y test. Okay. Finally, we want to see them on the plot, the scores. So take this code, you have train r squared and you have test r squared here. See your results on the side, see the distribution in the predicted value here. Okay. The next thing, we consider that we have just a value of lambda. In the previous model, we are going now to have the regression with different values of lambda. Okay. Let's say the alphas they go, they put the array here, the line space, from 0 to 100 by 10, for instance. scaling. Okay, we have lambda minimum equal 0.01 for instance. We have our lambda maximum, let's say 2. Then the number of lambdas, how many lambdas do you need? Let's say 110. So 0.01 to 2, and we have 10. So our lambdas will go from where? L min to L max by L num. Okay, so lambdas equal np space L min, L max, L num, the number of lambdas. So from minimum of lambdas to maximum of lambdas, the 10. For the prediction, how many numbers we need corresponding to the value of x is. So x dot shape okay. The coefficients we need also to store them. Coefficient as alpha and p dot zeros. They go to from the number of lambdas to the number of the prediction. Okay. We also need to add put R squares for train and the test. They also np dot zeros. So for each lambda we need an R square. So we have 10. So we have 10 R squares. So L num for train as well as for test. So R square test equals np dot zeros L num. Okay, now we have to look enumerate the iteration. Enumerating true lambdas with index and i's. Okay. So for IND, index I and enumerate lambdas okay. Our model, which is reach underscore flat equal is the reach. This time you have a lot of lambdas here, so alpha is going to be our I iteration, sorry, and we are going to fit it on X train, Y train. Then we need the coefficients also for each of them for the loop. Mainly equal the model coefficients dot coef then we also need R square on train and test during our iteration. This is equal the score teach underscore plot dot score on X train, Y train, okay, and testing data we would have the same index, but this time the score on testing data. Okay, so let's run and see, run everything. Okay, good. So now we are going to plot the R squares as a function of each lambda. So this will have the R square on train, R square on test, function of lambda. So we have a number of lambdas 10. So for each lambda we'll have a specific value. For example, for the alpha corresponding to the lambda from 1, 2, 3 up to 10, and each R square 1 to 10. So for testing and for training and testing data. So plotting the R square values as a function of lambdas. To do that, we need to import the library. The matplot lib.pyplot as PLT. Sorry, function module. Import matplot lib.pyplot as PLT. plot lip inline. Okay. Okay, after having these modules, we are going to plotting their squares. Okay, first thing we need is to have our figure size. So plt dot figure fig size equal, let's say 20 and 18, 20 by 18. Size plt dot figure fig size 20 by 18. Okay. After setting the size of the figure, we are going to plot our R-train. So plt dot plot R square on train, sorry. Plot the R square on train, which is here. The line type, and then we label it as R square and training data. Across the code, we give it a color as blue. So we alpha, the size equal let's say 0.6, and then the line width let's say equal 4. Okay, that's R square 0, 2, 4, 6, 8, and 10, no, lambda, and these are the corresponding R squares on the y-axis. Okay, maybe 2018 is too much, so let's say 8. Okay, figure size, yep, it's better. So on y-axis we have our squares, and the x-axis we have the lambdas. And we do the same thing for R square on test. So plt dot plot R square test. Line type, we take the same thing. Label equal R square, $sign here, testing data. Close the quotes here. Color equal red this time. Between the other arguments going to be the same. And then line width equal 4. Let's run line width. Okay, line width here. Sorry about that. Okay, so you have our two plots here. R square on test red, R square on training is blue. And then we are going to label now the axis PLT dot y label. We have R square. Take this, I think what good. So have R square on here R square. We are going to label the x axis we say regression, okay, R squared as a function in the code of lambda values. What X label? No. This is the title. I'm sorry. Let's say lambda values only. Yep. Now we have the legend. Legend. We ask her to put it at the best location. So if I look best, where is going to be the best location? For the upper right. Yep, evidence here. R square training data, R square testing data. And then we want to remove the grids here. So PLT dot grid okay, so you are done with the plot. So when you have different values of lambda, you have different r square for each of the values. So what we did here and what we practice here. So now we are going to make predictions. We train, we plotted the prediction errors, the residuals, the r squares, and training and testing data. Now let's go to making predictions. So let's call whitepad equal read is our model. Predict. We're going to predict on testing data. X, Y test. Oh, sorry. I'll predict on test data. I'll put again whitepad. Sorry, whitepad you are looking for here. Y test, sorry. So non-whitepad. These are the predicted values on our X test. It continues. We have 2,811, I think. No, 1,208 something. So now we are going to compute the R square of the prediction. For this, you need to import R2 square from scikit-learn.matrix. Okay, we run then. So logically we have the prediction on test score, so you need the R score on the prediction on test score on testing data. So let's call it this. R square right. Okay, let me change this. Okay, let's continue. Equal R2 score. We have Y test and the Y red. So now R square on test, we already had it before now. Let's again help us, sorry, again. .84%. Okay. So after making the prediction, we complete our score on test. We already got that before. If there is confirmation here that we are about 0.71%. So the next step to do is to complete the RMSE, the written mean square errors. To do this, we need to import the mean square error from scikit-learn.metrics. Okay, so already run. So we complete the RMSE on test, and then we do the same on train. We type RMSE on test. RMSE, let's call it RMSE test equal NP summary SQRT mean square error on white test white code. Then we call our object RMSE test to get the result. So this is the root mean square error testing. We can do the same on training as well, but to do that we need to predict on training before, because we need this spread on training. So that's why before I was hesitating on putting maybe here test. So white right here on test in data. So everything here you see is on test compared to test. Okay, now we RMSE on training data. Here we'll have first to make the prediction y red on train equal the model, the reach underscore float dot predict on x train. Okay. After making the prediction on training data to get our wildcat train, we are going now to computing the RMSE on train. So RMSE on train equal np dot square root of mean square error y train y pred train. And then have RMSE train okay. We are done with this part, so we are going to go to the model tuning. Model tuning using reach CV. To find the optimum alpha. That's the purpose. We need the optimum alpha here to choose in order to have a tuned model. To do this, we need to import the reach CV from scikit-learn.linear model okay. Now we are going to run our faithful cross validation for this. So reach the model front underscore CV equal reach CV alphas equal np dot random dot random integer bandit parentheses. We go from 0 to 100 10 comma CV equal cross validation, we take 10-fold cross validation, and we have dot fit. We fit on X train, Y train. Okay, this is our cross validation. Okay. Let me verify the code. Read float CV alphas array random integer 0 100 CV 10. Okay, good. Good. Let's count here. Okay, underscore. Hit for CV. Okay. Hope I run this. Let's see. Let's see. Okay. Underscore CV equal CV. Alphas equal np dot random dot round integer 0 100 10 comma CV equal 10. Yes. Dot fit X train, Y train, okay, random instead of random. Okay, good. Excellent. So we need to print the scores. Printing the scores. Which underscore flat underscore CV point alphas. This one is going to give us our alphas. So we take this another way, just type slash. These are the values of the alphas, the CV. This is the object here. Type the name of our object here. It's going to give us also the same thing, but a little bit more of information. So the array, alphas array. So the content is the same. Okay. Then when we need the optimum alpha. Okay. The optimum alpha is given by this code. We have this underscore. So the name of our model for the cross validation, reach underscore flat underscore CV dot alpha underscore. That is going to give us the optimal or optimum alpha, which is 15 here. Okay. So now we are going to take this alpha to create a tune model. So creating a new model with the optimum alpha. So let's call this model tuned. So reach flood underscore tuned equal reach parenthesis dot set params. We take alpha equal our optimum alpha. So this is our optimum alpha here. Reach dot underscore flood underscore c dot alpha underscore. Okay, then we fit on training and testing, X train and Y train. Okay, so we already have our tune model here. So next thing to do is to predict the tune model and the testing data. Okay, so we type y prep tune equal the name of our model, the new model now, reach underscore flood underscore tune dot predict test. Let's test. We run. The output, the predicted values, you see. Quite tuned. Okay, so the predicted values of the tune model. Okay, so we need to compute at least a metric on this. The RMSE, for instance, on the tune model. So RMSE tuned, let's call it RMSE tuned equal NP square root mean square error error y test y prep tuned. press H1 to see the value. Okay, so this is the RMSE on the tune model. Thank you for watching this video. I hope it will help you in your research. It's kind of a long video here, but yeah, I hope you get something from it. Plotting your residuals, the prediction errors, plotting your R squares. So thank you for watching.